Okay, so let us next discuss the empty set. And let's start our discussion with these two sets A and B. Let's first see what A is. A is the set of all elements X such that X is a student of class 11 presently studying in a school. Okay, now what is it about this set A? Say you have decided what the school is, which school we are talking about, say we have decided that. We then go over to that school and see who the students in class 11 are. And of course, there will be students. So, the characteristic of this set A is that there are elements in A. However, that is not the case with the second set B. Let us see what B is. B is the set of all elements X such that X is a student presently studying in both class 10 and 11. This, however, cannot happen. In no school will you encounter students studying simultaneously in both the classes. So that is why there is in fact no element in B at all, and B thus is empty. There is nothing in B. Such sets also exist, and this is one example. So the way we have these two different kinds of sets is that the first one of them has elements in it, but the second one has no element in it. The set B has no element in it. So it is empty, and with this idea we have our first definition of today. Definition 1. In the book it's given as definition 1, but because we are not really very careful in maintaining these numbers and whatnot, so if you want you can write definition 1 or you can just write definition. For us the concepts, the notions matter more than numbering them. Okay. A set having no element in it is called an empty set. Like this set. Okay, so this B is an example of an empty set. An empty set is sometimes also called a null set or a void set. These terms, however, are not really used. Okay, although these also they mean the same thing, an empty set. However, we normally do not use these terms. We use the term empty set to talk about a set which has nothing in it. We denote an empty set by the symbol this, or there is another way of denoting it using curly braces, because we use curly braces to enclose the elements of a set, whether we write the set in roster form or tabular form. We use curly braces, but then to indicate the fact that an empty set has no element in it, we just write the two curly braces and they are not enclosing anything. Okay, so that also gives us another way of denoting an empty set. So the other symbol looks like this or this. Just like the terms null set and void set are not really used, we normally say empty set, just like that, this symbol is the frequently used one and this symbol is not used at all. Okay. And now there is something I need to tell about the symbol itself. Some people confuse this symbol with the small Greek letter phi. This is not phi, and as such, it's not really nice to call it phi. Instead, when you see this symbol somewhere and you need to say it, you say empty set. And there is a difference also. You see, if I write phi and alongside, just next to it, if I write the empty set, do you see the difference? The difference is in that ellipse. In case of phi, the ellipse is like this, as if it's lying down horizontally. In case of the empty set, that ellipse is upright. In order to write the symbol of the empty set, what you do, you write the symbol for 0 and then strike it out. That is actually the symbol for empty set. And there is another thing that needs to be said at this point. Look at this indefinite article, an empty set. However, the heading says the empty set. What is this discrepancy? We will discuss about it, but not right now, because in order to turn n into the, we need to define equality of sets. That is coming. Okay. So after we have defined equality, then only we will discuss about this n and the issue. Okay, so we have already seen one example of an empty set, B. Now let us see some other examples. At this stage, because we have n empty sets, so maybe these empty sets are different empty sets. Who knows? But after defining equality, we will see that essentially they are actually the same set. So let us see these next examples. Let us see this A. Do not confuse this A with our first example of A. That is something else. Okay. So it is the set of all natural numbers x such that x is greater than 1 and less than 2. Is there a natural number that is greater than 1 and at the same time less than 2? No. Because in between 1 and 2, strictly there is no natural number. The natural number that comes right after 1, if one goes like that, is 2. There is nothing in between. I mean, as far as natural numbers are concerned. So that's why this set is empty. This is also another way of expressing that A is an empty set. That is by writing that it is empty. Next, number 2. Here also, do not confuse this set B with that example. It is the set of all rational numbers x such that x square minus 2 is equal to 0. If such a rational number exists, then its square must be equal to 2. But you know very well from your previous classes that no such rational number exists. So this set B also has nothing in it. That is why B is also empty. These are two more examples of empty sets. Oh, and there are others also. So let's see. There is a C. And what is C? Okay. It is the set of all elements X such that X is an even prime number. Even prime number greater than 2. Is there any even prime number greater than 2? No, because the only even prime number is 2. All the other prime numbers are odd prime numbers. This comes from the definition of prime numbers and even numbers, and of course because of that odd numbers. So C is also empty. And there is another one. D. It is the set of all elements X such that X square is equal to 4 and X is odd. You know what type of x's satisfy that equation. There are two x values. One of them is minus 2 and the other is plus 2. And both of them are even. So the square of no odd number can be equal to 4. And as such, the set D is also empty. There is nothing in it. So besides that first set B, these are 4 more examples of empty sets. Okay, next come finite and infinite sets. Let me use a ruler here. Will look nice this way. Alright, so to motivate the discussion of finite and infinite sets, let us first see some examples. Let's consider these sets. A consists of these 5 natural numbers. B consists of these letters from the English alphabet. Okay, and the set C is a little strange, but it is what it is. C is the set of, the way it has been written, this is really not correct. Let me write it correctly. C is the set of all x such that X is a man such that X is a man who is currently alive. Actually, the way it is given in the text is this: C is the set of all men living presently in different parts of the world. But of course, that set can also be written like this. Alright. Now we see that these sets have something associated with them, namely that you can start counting the elements of each of these sets, and the counting process will eventually come to an end. It will stop. For example, for the set A, if you start counting like this 1, 2, 3, 4, 5, the moment you hit 5, the counting process stops. And in fact, the elements here themselves help you in your counting, because they themselves are the natural number, first 5 natural numbers. In the second set, we do not have numbers, we have letters, but still you can count 1, 2, 3, 4, 5, 6. So the counting stops at some stage. And for the third set, the set of all men currently alive in the world, it's a large set, okay. However, here also, if one starts counting, that counting will eventually stop, although it may take a very long time to count, to finish the counting fully. But in all these sets, the counting process stops. And this is, this type of sets are called finite sets. And that thing that I was saying just now, that there are things associated with these sets, and that thing is the number of elements in each such set. And that number is denoted by n, and within parentheses you have the set. For example, n of A is 5. N of B is 6. What is n of C? We don't know. However, it will be quite a large natural number. A large natural number. So a set will be called a finite set if the number of elements in that set determined by this counting process is a natural number. 5 is also a natural number, 6 is also a natural number, like that this is also some natural number. We don't know what it is, but that does not matter. What matters is that it is a natural number. So such sets are called finite sets. And if a set is not finite, then it's called an infinite set. But that is not quite true. I have left out a case, and that case is the case of empty set. In case of an empty set, if one starts that counting process, then immediately one stops, because one does not encounter any element at all. In fact, the counting process does not start at all, so that the number of elements in an empty set is 0. Now for us, 0 of course is not a natural number. So you may say that, no, then the empty set is not, perhaps I should not say the empty set, because still we have no way of ascertaining that there is only one empty set. I should say an empty set. Okay, but anyway, the number of elements in an empty set is 0. But 0 is not a natural number. So this is one case which is a little different, but still it's considered to be finite, simply because the counting process stops. It does not in fact start at all. In the other cases, the counting process stops, but it starts also. Okay. So these are basically the finite sets, and any set which is neither like this nor is an empty set is called an infinite set, and that's how we also have our second definition. A set which is either an empty set or a non-empty set, but which has a definite number of elements, is called a finite set. But has a definite number of elements, which is a natural number, is called a finite set. Do you see why okay, but before that, do you recall that we said something about n when we first started our discussion? We said that for us, n is this set. However, for some people, n is this set. These are not the natural numbers for us. I mean, of course, these are, but not including 0. However, at that time I said that it's just a matter of saying or not saying that 0 is a natural number. It's simply a matter of calling 0 natural or not. We have decided to not call 0 a natural number. But if you do decide to call 0 a natural number, that is also okay. That is not a mistake. But you have to make sure which one of these two meanings you are considering. For us, this is not what n is. This is what n is. However, from this definition, you can see that perhaps if we decided to use this n, at least there would have been a uniformity in defining finite sets. Okay, just a thought. And a set which is not finite is called an infinite set. Okay. That means an empty set is also a finite set, and there are non-empty sets also which are finite. But of course, infinite sets also exist. But before leaving the definition, let's mention this also. For a set, for a finite set, S we denote by n of S the number of elements in S. Well, for an infinite, if S is infinite, then also you can use this notation n of S to denote the number of elements in S. In that case, however, you will always get this n of S is infinity. This, however, usually is not written. I mean, the fact that S is infinite is usually not expressed by writing this. We just simply say in words S is infinite. However, when S is finite, then this n of S takes on a definite value, and that value is not infinity. It is something like this, 5 or 6. And if your set is empty, then that value is 0. Okay. Oh, by the way, I forgot to say something when I was defining empty set. A set which is not an empty set is called a non-empty set. We will have something to say about this number of elements in a set, but it will take some time to reach that stage. Okay, we have to define union of sets, intersection of sets, and then there is a formula which gives us the number of elements in the union of two sets in terms of numbers of elements in the sets. Okay, so those things will come. But before that, let us see examples of finite and infinite sets. Alright, so the examples start like this. There are a number of them. W is the set of the days in a week. This set is finite, of course, because if you start counting the days, you eventually stop and you get this. The number of elements in W is 7. So W is a finite set. Then in the second example, what do we have? Yeah. S, the set of solutions of the equation x square minus 16 equal to 0. So we know what this set is. This set consists of these two elements, minus 4 and 4. So this is also finite because if you start counting minus 4, that is one element, and then 4, two elements, and the counting stops. So it's a finite set with n of s equal to 2. You can perhaps understand that at this stage, the exact rigorous mathematical definitions of finiteness, empty sets, all these things cannot be given. Right now, you are being given just some ideas, and see, the main aim right now is not to have rigorous definition, everything absolutely clear. That is not possible right now. Right now you just need the ideas, and you need to familiarize yourself with the ideas, so that later when you get the exact actual definitions, those things, then only you will understand them. So at this stage, if some things are a little vague, it's not a very big problem, it's okay. Let's just get our hands dirty with these things, and then only we will learn the actual thing. Okay, anyway, so S is also finite. Oh, and I would like to add one more set to this list of sets. Let us first write down what we have in the book. And then for some reason G, the set of all points on a line, a straight line. Now let me just draw a straight line. When we say line, usually it means a straight line. And you know from geometry that a straight line, though we may draw only a part of it, is unbounded on either side. It doesn't stop going on that side and it doesn't stop going on this side. And to indicate that fact, we sometimes use arrowheads on both sides. So what this set G is, it is the set of all points on this line. Can it be finite? No. Why? Because if you start your counting process, will that counting ever come to an end? Just think about it. Say you take this point for some reason and decide to count the points on this line. What will be the next point? You immediately find difficulty in this task of counting, because the next point can be any point other than this point on the line. After some thought, you may decide to leave this part which lies to the left of this point, and you say you decide to see what happens to the points which lie to the right of this point. But there also you encounter difficulty, because if you count the next point as this point, for example, but there are other points also, do you continue counting like this, deciding some distance as your unit distance and then following that distance, and you get more and more points? But the problem is that in that way of counting, you are missing points, you are leaving out many points in between. And you soon realize that you do not even have to go beyond this point, or say beyond this point, after counting these 2 points, because in between there lie many points. If you stop and you decide to first settle these points, there itself your life will be over, because the moment you see that there is a point in between these 2 points, there will be other points in between these 2 points, and there itself you will stay trapped. So from this you get an idea that no such counting can possibly stop. Okay, forget about stopping. You cannot even capture all the points within a finite part of this line. And that is why this set is infinite. Why am I stressing so much on this counting? That's because the actual definition of a finite set, and hence of infinite set, depends on a kind of counting. Technically, that counting, the apparatus that one uses to count sets, it has a name. It's called a bijective function or a one-to-one correspondence. But those things will come later. Okay, right now there is no need to worry too much about them. You just think about counting. G is infinite. Again, I could have expressed this fact by writing this, but I won't. because this is not how we usually express the fact that a set is infinite. And to this list of sets, I would also like to add this one so that we do not forget. An empty set is also finite by definition. Here the counting does not even start. For that itself it stops, and its number of elements is 0. There is, however, a more natural set which is infinite, and in fact that set does not involve geometry, means does not directly involve geometry. Let me just add those also. The sets of all natural numbers, integers, rational numbers, real numbers are all infinite. Okay, so these are some other examples of infinite sets. And after having these examples, the book then mentions something which we have already discussed about. It is that when we write a set in roster form, where we list the elements, if the set is really big, then we use those 3 dots, ellipses. But of course, if the set is infinite, then we have to use those 3 dots. For example, in order to specify this set in roster form, we have to use those 3 dots, and in some cases more than once. But again, let me remind you, only 3 dots, okay, not more, not less. And then there is an example of some more sets, and in this example we have to decide whether each one of them is finite or infinite. This is example 6. Maybe some other number in some other book, I don't really know, but that does not matter. The sets matter. In this example, we are being asked to decide whether each of these sets, which I am going to write now, is finite or infinite. And the first set is this. It is the set of all natural numbers x such that x minus 1 times x minus 2 is equal to 0. You see, you are immediately able to write this set down in roster form because its elements are 1 and 2. Of course, this is finite, and the number of elements in it is 2. The number 2 the set of all natural numbers x such that x square is equal to 4. You see, sometimes we become careless because of tiredness, fatigue, or maybe we are in a hurry to do something. Never do mathematics in a hurry. Always do it when you are relaxed and when you can think. Okay. See, the common mistake that may happen here is that the moment we say c x square equal to 4, those of us who take great care in finding out roots of equations, that is values of the variable x from an equation, they will readily write minus 2 and 2, forgetting that x has to be a natural number, and that is why minus 2 actually has to be removed. It's not a natural number, it's an integer, but we have been asked about natural numbers only. So this is also a finite set. And the number of elements in it is 1. Then the third one, it is the set of all natural numbers x such that 2x minus 1 is equal to 0. This set, however, is empty. Why? Because the only solution of this equation is x equal to 1 divided by 2. And 1 divided by 2 is not a natural number. It's a rational number, but it's not natural. So this set is empty, but nevertheless finite. And the number of elements in it is 0. Then number 4. Okay. The fourth one is the set of all natural numbers x such that x is prime. Yeah, this set is not finite. If one tries to write this set in roster form, after writing the first few primes, one has to use ellipses to complete writing the set. One finds the proof of this fact that there are infinitely many primes. I am not sure, I don't remember whether this proof is in school, has it already appeared, or you are yet to see this, but the proof is not really that difficult. It can be found in number theory. It is by Euclid that there are infinitely many primes. But the fact is that there are infinitely many, and so this is an infinite set, because if you start counting, the process never stops. So this is an infinite set, and as such the number of elements in it is also infinite. And there is one more. This is also the set of all natural numbers such that x is odd. Well, this set is not as complicated as the set of prime numbers. It is easy. In fact, we know the pattern in which the numbers appear, but this is also infinite. The odd natural numbers also do not stop. They keep coming. So this is also infinite. And finally, we come to the notion of equal sets. This will be the last thing we discuss tonight. After defining what it means for two sets to be equal, then only we will go back to the issue of there being only one empty set, and then we can write the empty set. Two sets A and B are said to be equal if every element of A is in B and every element of B is also in A. And that is quite natural, because for two sets to be equal, we would want them to have precisely the same things, same elements. And a way of expressing that is this: and every element of B is also in A. And an easier way of saying this is in this next definition of the same thing. Two sets A and B are said to be equal if they consist of exactly the same elements. So you can clearly see how this and this are in fact the same thing. When A and B are equal, we write naturally enough A equal to B. Otherwise, we write A not equal to B. Okay. Now, the condition given in definition 3 is easier to understand. We said that two sets A and B are equal if they consist of precisely exactly the same elements. However, it takes a little thought to understand this part. We say that A and B are two equal sets if every element of A is also in B and vice versa. Every element of B is also in A. Let's see how that works. Okay. Suppose this is your set A and this is your set B. This is just for the sake of discussion. Alright, so I am not going to say what these circles really mean. You can roughly imagine it like this. The circle denoting the set A, actually it encloses the elements of A within it. Okay, so the elements of A lie here somewhere. Similarly, the elements of B lie here somewhere. Had these two, so the way we have drawn this figure, obviously these two sets are not equal, because these are some points that you see which are different, and these are some points which are also different. For them to be equal, there should be only one circle. So they should consist of precisely the same elements. And in that case, every element of A is also an element of B, and every element of B is also an element of A. Let us also see what happens if this condition is not exactly true. Let us think of a situation like this. It is a situation in which every element of A is also an element of B, but there are some elements in B which are not in A. In that case, these two sets are not equal. Okay, and being not equal means having this, or for example, this. Here, every element of A is not an element of B. In fact, no element of A is an element of B. That alone tells us that A is not equal to B. But at the same time, let's also observe that no element of B is also an element of A either. Alright. This means that in order for two sets A and B to be not equal, either there should exist at least one element in A which is not in B, or there should exist at least one element in B which is not in A. So that is the notion of equality. Equality is almost trivial, but two sets being not equal takes some thought. Okay. Now, with this understanding, let us go back to the issue of having only one empty set. Suppose hypothetically that there are two empty sets. 2 means there may be more, but we have found 2. One of them is this and the other one is this. And say you decide that no, they are not equal. This means what? This means that either there exists some element in the first empty set which is not in the second empty set. That we can of course express in the language of set theory. Either there exists X belonging to the first empty set such that X is not in the second empty set, or there exists some element Y in the second empty set such that Y does not belong to the first empty set. That's what two sets not being equal means, and that's what it means in this particular case. Now let us see what we can next say about the current situation. It's an either or statement, and an either or statement is true if either of the two parts of it is true or both are true. Is the first part true? Can it be possible to find an element X in the first empty set which is not in the second empty set? No. Why? Because the first empty set is empty. There is nothing in it. So how can you find such an X? And that is also the case with the second part. It is impossible to find a Y in the second empty set simply because the second empty set is also by definition empty. And that is why there is no, there is nowhere to go. Both of these are impossible, and as a result, this is also impossible, which means that we are forced to conclude this. So if you have two empty sets, actually they are the same, and that is why there is precisely one empty set. And in fact, that is why it makes sense to denote that empty set by this single notation. Otherwise, if there were more than one empty sets, then one notation would not work, of course, because you would need new names to name them, but there is only one, and that is why a single notation. Okay, so this is the reason for calling, for saying the empty set, not an empty set. All right. So now next there are some examples, so let's see those examples of equality of sets, not non-equality or inequality of sets. And after defining equality of sets, there are some, before examples 7 and 8, there are in general some examples. Let us look at these two sets to illustrate the notion of equality. 1, 2, 3, 4, and the set B 3, 1, 4, 2. We know that in writing a set in row star form, it does not matter the order, the order in which we write the elements, that does not matter. What matters also by the definition of equality, that every element in one set should be an element in the other, and vice versa. Is 1 an element here? Yes. Is 2 an element here? Yes. 3 is an element here, 4 is an element here. So every element of A is in B, and like that every element of B is also in A, and that is why A is equal to B. And there is another one. A is the set of all prime numbers less than 6, and B is the set of all prime factors, I think. Where is it? Yeah. Set of all prime factors means positive prime factors. Because we are saying prime, so no need to mention positive. All prime factors of 30. You know that the prime numbers less than 6 are 2, 3 and 5, and they also turn out to be precisely the prime factors of 30. Why? That's because 30 is 2 times 3 times 5, and that is why A is equal to B. These two sets, although the way we have described or defined them, they look different, but ultimately they consist of precisely the same elements, and those elements are 2, 3 and 5. Okay, so let us next see example 7. In example 7, 5 sets are given. From among them we have to see which are equal to each other. Okay. and those 5 sets are these. The first one is this A, and then we have B, x such that x is greater than 15 and at the same time x is less than 5. C is the set of all x such that x minus 5 is equal to 0. Next, D. It is the set of all x such that the square of x is 25, and there is one more. E. X such that x is an integral means it's an integer, integer is noun, integral is adjective. Positive root of the equation. A quadratic equation, and it is x square minus 2x minus 15 is equal to 0. So in order to decide which sets among these are equal, let us decipher the sets, so to speak, by actually finding their elements. Okay, let me write here. A is, of course, already we have the element, only element in A. What is B? B is the set of all x, of course, a number such that x is simultaneously greater than 15 and less than 5. Is that possible? No. And that is why B is the empty set. Note that now we can say the empty set. Next, C. C clearly consists of only 5. Then D. D consists of minus 5 and 5. And what about E? E is the set of roots, but integral positive roots. So we need to solve this quadratic equation. Let's use that formula. Using that formula without saying much about it, we already know. We will find the roots. So what are we getting? 64, that means 8. So after dividing by 2, we get this. So one of the roots is 5 and the other root is minus 3. But keeping in mind that we need, see, both the roots are integral, they are integers, but we need positive. And that is why E is equal to 5. This way it's easier to see which one of them are equal. They are all different from one another except C and E. So the only equality equation is this. Every other set is different from every other set. And in fact, C itself is also different from the others. And finally, we have another example. Example 8. In this example, pairs of sets are given and we have to see whether they are equal. The first pair has these two sets. X is the set of letters of the word alloy. And Y is the set of letters of the word loyal. If you really write these sets down in roster form, then you will see more easily if they are equal. So what are the letters? We have A, L, O and Y. And there is no point repeating letters. We have already discussed about that. Repeating letters is allowed, but that does not serve any purpose. What about Y? L, O, Y and A. And here we won't repeat L. Okay, so A, L, O, Y. Yes, they are equal. And there is one more pair. Number 2. A is the set of all integers n such that n square is less than or equal to 4, and B is the set of all real numbers such that x square minus 3x plus 2 is equal to 0. Alright. Now, in situations like this, it's not always advisable to blindly first find all the elements in the sets, because you do not know whether they are equal. Maybe they are not equal, and in that case, it's enough to show just that there is one element in one of these sets which is not in the other. That itself would make you conclude that they are not equal. For example, if you think about it, you may notice this fact. Since 0 belongs to A, but 0 does not belong to B, we have A not equal to B. Just to decide that the sets are not equal, this much is enough. Let us now see how these are true. Why is 0 in A? Because the square of 0 first of all is an integer, and its square is 0, which is less than or equal to 4. It's less than 4 actually. So that's why 0 belongs to A. 0 does not belong to B because 0 is not a root of this equation. If you put x equal to 0 here, you get 2, not 0. That's why 0 does not belong to B. But however, just for the sake of it, one can note that the elements in A are these. How we find these elements, I am not going to say anything about that. Okay, you figure that out yourself. How you solve this inequality, keeping in mind that n is an integer. And just like that, the elements in B are 1 and 2. This, however, you know very well how to find. You just have to solve this equation. And that's how this section ends. After that we have exercises which we will solve in the community section. And this time we will do it day after tomorrow itself. Okay, and from now on there will be 2 videos per week, one on Tuesday and one on Thursday. So that's just it for tonight. So see you on Thursday in the community section. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.